Suppose one day you realize that perhaps the things you once absolutely believed about the universe were not accurate. From the very beginning, what then? Every morning when you open your eyes, and when night falls and you drift into sleep, you rarely question the world around you. The ground beneath your feet seems solid. The sky stretches above your head. Time flows in a familiar direction, never reversing. All of this creates the feeling that reality is stable, clear, and trustworthy. Yet modern physics is gradually shaking those seemingly certain assumptions. Results from quantum mechanics have led many to ask, is reality truly as stable as we once thought? Some viewpoints even suggest that the universe might resemble an illusion, a vast performance, deceiving our light and our perception. Let us step into the discoveries that have compelled humanity to seriously question whether the universe truly exists in the familiar sense we have always understood. The Einstein-Podolsky-Rosen paradox. Is the universe truly local? In 1935, Albert Einstein, together with Boris Podolsky and Nathan Rosen, proposed a thought experiment, later known as the EPR paradox. Their goal was to highlight the strange consequences of quantum mechanics, especially the idea that particles could be connected in ways that seemed unacceptable from the standpoint of classical physics. The central question they posed was, does the universe possess locality? In other words, is everything influenced only by events occurring in its immediate vicinity? Or is there a deeper and more mysterious mechanism at work in everyday life? The world feels entirely local. When you push a chair, it moves because you touch it and apply force. An object does not naturally respond to something far away unless there is a specific connection, such as a string linking the two. Locality sounds reasonable because it matches our direct experience. Objects exist in space, and their behavior appears limited to their surroundings. But the EPR paradox casts doubt on that obviousness. It suggests that particles may interact in ways that go beyond the familiar local model. Einstein and his colleagues found it difficult to accept the concept of quantum entanglement. Two particles that once interacted could remain connected regardless of how far apart they are separated. When you measure the state of the first particle, the other seems to adjust instantly, even if it is light years away. This gives the impression that information has traveled faster than light, contradicting relativity, one of the very foundations Einstein himself helped build. And it leads to an uncomfortable question. How can two objects, separated by such vast distances, remain so tightly bound together? Einstein called this phenomenon spooky action at a distance. The purpose of the EPR paradox was to show that quantum mechanics might be incomplete. Einstein, Podolsky, and Rosen believed that there must exist hidden variables, unidentified factors that could explain the seemingly irrational behavior of entangled particles. If these hidden variables were found, the universe would return to its familiar image, operating through local, more understandable interactions. However, quantum mechanics did not offer such a simple resolution. According to the theory, entangled particles genuinely behave in ways that defy locality. When one particle is measured, the other reacts instantly, regardless of distance. No clear explanation through local influences or classical-style hidden variables seemed possible. From this point, the scientific community began to divide into two directions. One side, like Einstein, believed quantum mechanics lacked a deeper foundation. The other accepted that the universe might be far stranger than intuition suggests, and that non-local connections could be fundamental features of reality. For decades, the EPR paradox had no definitive answer. Yet it ignited a profound debate, forcing physicists to re-examine the foundations of their field and to confront the possibility that reality is not as simple as we once believed. This shift in thinking became a major turning point in modern physics, paving the way for further theories and experiments that continued to challenge the classical view of the universe. Bell's theorem. From philosophical debate to experimental test. The turning point arrived in the 1960s with the work of physicist John Bell. Building on the EPR paradox, Bell proposed what later became known as Bell's theorem, a groundbreaking contribution that transformed the issue from a theoretical debate into something testable by experiment. Bell's theorem provided a concrete mathematical framework, through Bell inequalities, to test whether local hidden variables could exist. If Einstein were correct, these inequalities would hold. If quantum mechanics were correct, they would be violated. In 1972, John Clauser and Stuart Friedman conducted the first experimental test of Bell inequalities. This was the first significant step in measuring whether the behavior of entangled particles could be explained by local hidden variables. By 1982, Alain Aspect and his team in France performed a more refined experiment, and the results showed clearly Bell inequalities were violated. This meant that no local hidden variables exist that are sufficient to explain the behavior of entangled particles. Separated particles can still relate to each other instantly, as though space and time no longer function in their familiar way at the quantum level. Einstein had died in 1955, so he did not witness these results. But had he known, it might have been a difficult conclusion for him to accept. He had hoped that deeper understanding would return physics to a local and predictable universe. Instead, Bell's theorem and subsequent experiments reinforced the idea that the universe appears fundamentally interconnected in ways classical physics cannot explain. From a loophole that EPR sought to expose, the paradox became one of the strongest pieces of evidence supporting quantum mechanics. The universe as an illusion we live through our senses. We trust what we see, hear, and touch as real. A tree trunk appears solid. The sky is blue. Gravity holds us to the ground. These experiences construct a world that feels stable and predictable. But what if reality is not as solid as it appears? What if what we perceive is only a layer shaped by the mind? Since the time of Plato, philosophy has debated whether the world exists independently of our perception, or whether perception itself shapes the world. Plato suggested that what we see are merely shadows of a deeper reality. Quantum mechanics makes this debate more urgent. At extremely small scales, particles can exist in multiple states simultaneously. They do not have definite positions until measured. Before observation, they exist as clouds of probability. Only when we measure does the state collapse into a specific value. If reality only takes form when observed, does it exist independently of us? Schrödinger's cat experiment illustrates this strangeness. Inside a sealed box, the cat is both alive and dead until someone opens the box to observe. Only then is the state determined. This idea raises a profound question. What role does the observer play in shaping reality? Some Eastern philosophical traditions, such as Buddhism, speak of Maya, the illusory nature of the world. According to this view, what we perceive through our senses is not ultimate truth, but merely a veil covering a deeper reality. In a certain sense, modern physics seems to suggest something similar, that the universe we experience may be only a surface layer, beneath which lies a structure far more complex and counterintuitive. Technological implications and a deeper question. Quantum entanglement is not merely a strange concept in textbooks. It forms the foundation of quantum computing and quantum cryptography. In quantum computers, entangled particles can process information in ways far beyond classical machines. In quantum cryptography, any attempt at eavesdropping disturbs the entangled system and is therefore detectable. This leads to an even bolder thought. Perhaps information itself is the most fundamental foundation of the universe, even deeper than matter or energy. So, what is quantum entanglement really telling us? In classical physics, events are separated by space and time, and cause and effect relationships unfold in clear order. But at nature's deepest level, that separation no longer seems absolute, and perhaps the most astonishing realization is not how strange the universe is, but that what we call reality may only be the outermost layer of something far deeper. If you throw a stone into a pond, ripples spread outward from the point of contact. We can trace the chain of events back to the clear cause. The stone, cause and effect in the familiar world are transparent and always bound by space and time. But when we step into quantum entanglement, that connection suddenly becomes slippery and hard to grasp. Imagine two entangled particles, one on Earth, one on the other side of the galaxy. When you measure the particle on Earth, The distant one seems to match its state instantly to align with the measurement result, even though the distance is so vast that no signal could travel between them in the usual way. This instantaneous correlation does not operate according to the space-time rules of the classical world. It suggests that the two particles are linked by a deeper layer of connection, as if they remain a single system. No matter how far apart they are separated, the first thing quantum entanglement shakes is our understanding of causality. In classical intuition, causes happen first and effects follow. In logical sequence, yet with entangled particles, measuring one seems to touch the other instantly, without any clear causal bridge in between. This opens the possibility that at the deepest foundational level, the universe may not obey the rigid cause and effect system we observe in daily life. Some physicists suggest that entanglement points toward a reality in which space and time are not fixed, perhaps not even fundamental, as we once assumed. From this perspective, entangled particles are not sending signals faster than light. Instead, the very notion of distance between them becomes meaningless. They belong to the same system. The sense of separation is merely an illusion born from our limited understanding of space and time. Viewed this way, quantum entanglement feels like a whisper that the boundaries we perceive between objects, between events, even between slices of time, may not be as real as we imagine. This is difficult to accept because it contradicts nearly everything we assume about the world, that objects are separate and distinct, that a tree is not a stone, that someone on the other side of the earth has no invisible thread directly connecting them to you. Yet entanglement suggests that such separations may be true only at the surface level. At a deeper layer of reality, the universe may be far more tightly interconnected through invisible links beyond our familiar spatial intuition. Another way of thinking emerges. Perhaps reality is not assembled from separate objects, but from relationships. In classical physics, we imagine the universe as a collection of independent objects, each with its own properties, moving through space and time. But in the quantum world, objects cannot be fully understood in isolation. Their properties only become meaningful in relation to others, especially when entangled. This suggests that the fundamental unit of reality may not be the thing, but the connection between things. We also tend to believe that we ourselves are separate individuals apart from the world. But if at the deepest level everything is interconnected, then the boundary between self and other may not be as sharply drawn as we think. Some philosophers therefore speculate that quantum entanglement may hint at a new way of viewing consciousness and existence if particles can connect across space. Might consciousness belong to a larger fabric of connection as well? Another puzzling aspect of entanglement concerns information. This phenomenon has led some physicists to ask whether information is the most fundamental element of reality, rather than matter or energy. Certain theoretical approaches suggest that the universe may be built from information, and that quantum entanglement is simply a way that information is distributed and shared across cosmic scales. If that is true, the boundary between the physical and the non-physical becomes even more blurred. For information, unlike objects, is not bound in the same way by space and time. It can exist in multiple forms. And entanglement may offer a brief glimpse into how information operates at the deepest foundational layer of the universe. And so entanglement brings us back to a question raised earlier, the role of the observer in shaping, which returns us to the most crucial point: reality. In classical physics, an object's properties exist independently of whether we look at them or not. An object is what it is, even if no one measures it. But in quantum mechanics, the act of observation becomes decisive, especially for entangled systems. Before measurement, a particle exists in superposition. Its properties are not yet locked into a fixed value. Only through interaction and measurement does the state collapse into a definite outcome. Beyond Einstein, when quantum mechanics shakes space-time, quantum mechanics and Einstein's theory of relativity, especially general relativity, are often regarded as the two pillars of modern physics. Yet they describe the universe in two very different languages. According to Einstein, the universe is a continuous fabric of space and time. Space-time. Upon this fabric, massive objects such as stars and planets move. Mass curves space-time. And that curvature is what we experience as gravity. This framework explains the large-scale universe with extraordinary effectiveness, from planetary orbits to galactic motion. But quantum mechanics working in the microscopic realm tells a different story, one that makes us question space and time themselves. The fundamental difference lies in how the two theories treat space-time. In relativity, space-time is continuous. It can stretch and curve, but it has no cracks. Objects move through space-time along smooth trajectories. Speed and gravity can change the rate at which time passes. Time runs slower for someone moving near the speed of light, or for someone close to an extremely massive object like a black hole. This phenomenon is time dilation, an important prediction of general relativity, confirmed by many experiments. By contrast, in the quantum world, space and time no longer appear smooth in that way. At the smallest scales, they seem to be granular, broken into discrete units like pixels. In that strange picture, particles can appear and disappear, and they do not necessarily move along continuous paths. Instead, they can jump from one position to another via quantum tunneling. This conflicts with the smooth, predictable space-time of general relativity. Therefore, one of the most thorny problems in modern physics is how to reconcile these two pictures. A classic example of that tension is the black hole. According to general relativity, a black hole is a region of gravity so strong that even light cannot escape. At its center is a singularity where space and time are said to collapse completely. But quantum mechanics suggests that this cannot be the whole story. In the quantum world, information cannot be destroyed. Meanwhile, general relativity implies that everything falling into a black hole, including information, could disappear forever. This contradiction becomes the black hole information paradox, a direct collision between quantum law and the predictions of general relativity. Not only that, phenomena like quantum entanglement and tunneling also push against classical space-time intuition. As we have seen, entangled particles can match states instantly across vast distances, something that seems to conflict with a basic principle of relativity. Nothing travels faster than light. In relativity, locality is foundational. Something here cannot influence something there unless a signal or force travels between them, and that signal cannot exceed the speed of light. But in quantum mechanics, that principle no longer holds in the familiar way. Entangled particles behave as if they are one unified system, regardless of spatial separation. And even time, in quantum mechanics, does not necessarily flow smoothly as we experience it in daily life. At extremely small scales, time can look like a sequence of discrete moments. Some physicists suggest that time may be quantized, meaning there could be a smallest indivisible unit, similar to how energy is quantized in quantum mechanics. This is very different from relativity's continuous time, where time resembles a smooth stream. Physicists have worked for decades to reconcile quantum mechanics and relativity, but so far there is still no complete unified theory. One prominent candidate is string theory, which proposes that particles and forces arise from tiny vibrating strings. In this view, space and time are not the final foundation, but something that emerges from a deeper layer of vibration. Another approach is loop quantum gravity, which suggests that space and time are made of tiny loops. At the quantum level, the fabric of space-time is granular, not smooth. If space and time are not the ultimate foundation, but only something that arises from the quantum world, then the universe we live in may be only one layer of a far more complex reality. The classical world, orderly and predictable, is built upon an indeterminate quantum layer, where familiar rules of causality, distance, and even time itself begin to fracture. Nobel Prize in Physics 2022, confirming that the strangeness is real. In 2022, the Nobel Prize in Physics was awarded to three scientists, Alain Aspect, John Clauser, and Anton Zeilinger, recognizing the key experiments that demonstrated violations of Bell inequalities. The experiments of Clauser, Aspect, and Zeilinger not only confirmed the strange predictions of quantum mechanics, but also profoundly changed how we understand the universe. by showing that Bell inequalities are violated. They demonstrated that the classical notion of an objective and local reality, where objects have definite properties and influence each other only through nearby interactions, does not accurately reflect how the universe operates. These results both strengthened quantum mechanics and pushed forward unanswered questions. If space and time are no longer as fundamental as we once believed, then what lies outside them? And how can we connect the smooth space-time of general relativity with the non-local behavior of quantum mechanics? These are still questions physics continues to struggle with today, and the work of Clauser, Aspect, and Zeilinger has provided important clues for tracing those mysteries. In a broader sense, Nobel 2022 did not only honor 3 individuals, it marked a major shift in how humans view the universe. One, represented by these achievements, quantum mechanics has long been famous for being hard to grasp and counterintuitive, but those experiments show the strangeness is not only in the equations, it is a fundamental feature of the world we live in. John Clauser paving the way for a quantum world without local hidden variables. In the 1970s, John Clauser's work created a turning point, bringing quantum mechanics from theoretical debate into experimental testing. At a time when the strange predictions were still doubted, Clauser's experiment brought abstract ideas into the laboratory, producing data strong enough to confirm or reject the core claims of quantum theory. The focus of the debate then was local hidden variables. In classical physics, people often believe that objects already possess definite properties: position, momentum, energy, whether or not we measure them. This belief is often called realism. The physical world exists independently of observation. Quantum mechanics challenges that assumption by saying that at microscopic scales, a particle can exist in superposition many possibilities at once, collapsing into one state only when observed. This made many physicists uneasy, including Einstein, who objected with his famous remark that God does not play dice with the universe. Einstein believed there must be hidden variables, factors we have not seen or measured, determining the seemingly random behavior of quantum particles. Bell's theorem, 1964, provided a way to test that idea through Bell inequalities. We can see whether local hidden variables can explain the data. Clauser accepted the challenge with a real experiment. Together with Stuart Friedman, he designed an experiment in which entangled photon pairs were emitted from the same source, flying in opposite directions to 2 detectors. According to quantum mechanics, once 2 photons are entangled, a measurement on the first photon will instantly lock in the correlated state of the second, no matter how far apart they are. To classical intuition, this is almost impossible, because no signal is allowed to exceed the speed of light. So what could make 2 particles so far apart they seem untouchable still match? Almost instantly, Clauser, putting the prediction of entanglement on the experimental scale. John Clauser's experiment was among the first times this prediction was tested directly. He measured the polarization of 2 photons, then compared the degree of correlation between the results. From the data, Clauser and Stuart Friedman calculated whether those correlations violated Bell inequalities, and they did violate them. This meant the observed correlations between 2 entangled photons cannot be explained by any model based on local hidden variables. In other words, there is no classical style mechanism where each particle carries only its own local information that can produce such strong agreement. The result pushed us toward a sharp conclusion. Quantum mechanics is correct as predicted, and entanglement is not merely a paper and pencil inference. Clauser's work turned what had been seen as hard-to-believe mathematics into a measurable, testable phenomenon. What Einstein called spooky action at a distance was no longer a sarcastic phrase. It became something present in experimental data. And the consequences did not stop at entanglement. It struck directly at the foundational question: by what principle does reality ultimately operate? If there are no local hidden variables, then quantum behavior is not governed by a classical machine underneath. Instead, measurement outcomes are genuinely random, following only the probabilities predicted by quantum mechanics. From here, the view of the universe changes deeply. Classical physics often treats the universe as deterministic. The past locks the present locks the future. But in the quantum picture, indeterminacy and randomness become fundamental ingredients. Not only that, Clauser's experiment also forced people to reconsider the role of the observer. In the classical view, measurement merely lifts the curtain on properties that already exist, but in quantum mechanics, observation seems to play a more active role in theory. Measurement collapses the wave function, taking a system from an undefined state to a defined outcome. This suggests that, at least at the quantum level, reality is not completely separate from the act of observation. The observer plays an important role in settling the result. Alain Aspect, sealing the loopholes in Bell tests. Alain Aspect's experiments in the 1980s made the evidence for quantum non-locality harder to dismiss. Aspect's goal was not only to repeat earlier tests, but to refine the design to eliminate doubts and close the gaps that critics could use to object. As a result, he and his collaborators strongly reinforced the conclusion that the behavior of entangled particles cannot be explained away by hidden variables, or by some form of secret communication between particles. Earlier experiments like Clauser's were very persuasive, but skeptics could still argue that some hidden factor might be influencing the outcome. Such gaps are called loopholes. The locality loophole. In many older designs, detector settings were chosen in advance of the photons being emitted. This raised a question: could the particles know in advance the detector settings and coordinate outcomes? If during the process, the particles somehow exchanged information by some unknown mechanism, one could argue that strong correlations do not necessarily come from quantum nature, but from a kind of hidden communication. Aspect addressed this with a key move changing detector settings while the photons were already in flight. Instead of fixing the settings from the start, he introduced randomness into the experiment, changing the settings only after the photons had been emitted and were on their way to the detectors. This largely removed the possibility that the particles could know in advance, effectively closing the locality loophole, and the result still did not change even when settings were switched randomly mid-flight. The data still violated Bell inequalities. This provided strong evidence that no local hidden variables or classical-style secret communication was controlling the experiment. Aspect's technical achievement was also remarkable. Photons move extremely fast, so switching settings within such tiny time windows demanded precise synchronization and advanced technology coordination not previously achieved in such tests. The detection loophole aspect also faced another problem: not every photon is detected. If detectors miss many particles, skeptics could claim that the measured data is only a biased sample. The detected photons violate Bell, while the undetected ones might behave classically. So he improved detector efficiency to reduce the number of missed particles, raising the fraction of photons actually measured and weakening the biased sample argument. And again, the more tightly the loopholes were closed, the more robust the Bell violation remained. That reinforced the idea that quantum non-locality is not a technical error, but a deep feature of nature. The more loopholes were sealed, the stronger the evidence for quantum mechanics became, and the more classical intuition was challenged. Anton Zeilinger and quantum teleportation, bringing entanglement into information processing. If Clauser and Aspect helped confirm that entanglement is real, Zeilinger took a natural next step. If entanglement creates a special connection, can we use it to transfer a quantum state without direct physical contact? The answer is yes, and that concept is called quantum teleportation. Of course, this is not the science fiction idea of an object disappearing here and appearing there. What Zeilinger and his team demonstrated is that we can transfer the quantum state of a particle from one location to another, using entanglement as a channel for that transfer. Because photons are easy to manipulate, Zeilinger often used photons. In a typical teleportation scenario, there are three particles, two entangled particles A and B, and a third particle C that carries the state to be teleported. First, C interacts with A, binding A's state to the information in C, because A is entangled with B. B then takes on a corresponding related state, even though C and B never interact directly. In this way, the quantum information about C's state is transferred to B. In short, C's quantum state is teleported to B. The key point: the material particle C does not go anywhere. Only the information about its quantum state is transferred. And this is where an important principle appears, the no-cloning theorem. Quantum mechanics says you cannot create a perfect copy of an arbitrary, unknown quantum state. Teleportation does not break this rule, because the original state, in a certain sense, no longer exists intact at the starting point once the teleportation process is complete. What seems like a small detail is actually a major boundary. It reveals how deeply the quantum world differs from classical intuition. In everyday macroscopic life, copying information is normal. In quantum physics, the rules of the game do not allow it in the familiar way. Teleportation operates within those strange rules you cannot perfectly duplicate. But you can still transmit that very state across space using entanglement. In a later experiment in Dois Zeilinger and collaborators teleported the quantum state of a photon across more than 143 kilometers between the Canary Islands. This showed that teleportation is not only a short-range laboratory idea, but can be carried out over significant distances. That result also strengthened the idea that entanglement can remain stable when particles are widely separated, and it opened the door to technologies such as quantum communication and quantum networks, systems that could change how we transmit data, moving toward channels more secure than classical methods. From here, an idea increasingly rises. Perhaps information is not merely a property of physical systems, but something more fundamental. Some physicists begin to speculate that information may be the deepest building block of the universe, deeper even than particles or energy. From this viewpoint, reality resembles a vast network of information, while objects and particles are simply manifestations of that underlying structure. What does violating Bell inequalities ultimately tell us? The violation of Bell inequalities is considered one of the most profound results in modern physics, because it forces us to reconsider how we understand the universe and touches the question, what is reality? Really? In Bell tests, when entangled particles are measured, scientists find correlations so strong that they cannot be explained by any local hidden variable theory. Once the classical escape route is blocked, we are left with uncomfortable options. Either locality, as we understand it, is wrong at a deep level, or nature operates in a way even stranger than intuition. A simple way to picture this is to imagine two coins. If you flip two completely independent coins, their outcomes will not be related. Sometimes both are heads. Sometimes both are tails. Sometimes one is heads and the other tails. And over time, you get the familiar distribution. But now imagine that every time the first coin lands a certain way, the second coin instantly produces the exact corresponding result, no matter how far apart they are. Your intuition would immediately say the two coins are connected in a way that contradicts the classical model. That feeling is close to what physicists observe, with entangled particles correlations stronger than what should be possible if each particle operated only with its own local information. Violating Bell inequalities not only suggests that locality breaks down at the quantum level, it also supports a deeper idea at the foundation. Reality may not be made of solid, stable objects, but of probabilities and relationships. Particles seem to lock in a state only when observed. Before that, their properties exist in an in-between condition. And this is what makes many people uneasy. Perhaps the universe is not real in the way we usually imagine. If a particle has no definite property until measurement, then what does the universe look like when no one is watching? Does the moon exist when no one observes it? Or does it only freeze into a definite reality when there is a measuring interaction? It sounds like philosophy, but it rises from experimental data. Bell violations force us to confront the possibility that observation is not merely passive information gathering. It may be a process that helps shape reality. At the center of all of this is non-locality. In classical physics, an event here cannot instantly affect a faraway place because nothing exceeds the speed of light, exactly as relativity emphasizes. But Bell violations show that at the quantum level, that limit does not operate in the way we expect. Entangled particles correlate instantly, not in the sense of sending a signal in the classical way. No message is traveling from one particle to the other, yet their correlations still appear clearly and occur faster than light could travel between the 2 points. This is what people call quantum non-locality. An event here can be tightly linked to an event far away without any physical connecting thread in the classical sense. A non-local universe, or a universe that does not exist as we think, when Bell inequalities are violated. It pushes us toward 2 possible interpretations, and both pull us away from familiar intuition. The universe is truly non-local. What happens in one place can be instantly linked to what happens very far away. The universe does not exist the way we think. Reality is no longer an objective, fixed, independent background in the classical model. Both options are uncomfortable for intuition. But if we take decades of experimental evidence in quantum mechanics seriously, they are hard to avoid. If non-locality is real, space-time may not be the foundation. If we accept non-locality, it implies the universe is tied together in a way beyond classical understanding. In that case, the fabric of space-time, so solid and orderly at human scales, may not be the correct framework at quantum scales. Instead of objects separated by distance and moving through time along a linear track, particles may connect across vast separations, as if the space between them is not truly important. Non-locality also suggests that correlation can happen faster than light. In classical physics, relativity sets an absolute limit, the speed of light. Nothing can exceed it. But quantum entanglement does not follow that rule in the way we're used to interpreting it. This does not mean we are sending usable information faster than light, but it does mean our intuition about space and time is incomplete at the quantum level. One interpretation is that the universe is connected at a deep level by a mechanism we do not yet grasp. Perhaps space and time are not fundamental bricks, but properties that emerge from something deeper. Then the universe is no longer a set of separate objects moving through space. It is a network of relationships and interactions, and those relationships are not limited by what we call distance. In other words, locality, the belief that things only influence nearby regions, may not be a universal law in the quantum realm. An even bolder picture is that space itself might be a kind of illusion, or at least not fundamental. The distance we perceive could be more like a consequence of how the brain interprets information than the deepest property of the universe. In this direction, entanglement correlations happen at a distance because, at the foundational level, the particles are not truly separated by space. Space emerges from an underlying quantum reality rather than existing as the intuitive stage we normally imagine. If the universe does not exist as we think, reality may depend on observation. An even more unsettling possibility is that the universe does not exist in the traditional sense of classical physics. Quantum mechanics makes some physicists and philosophers doubt, is reality objective? Or does it depend on observation? In classical physics, we assume objects have definite properties, but quantum mechanics says a particle does not have definite properties until it is measured. Before observation, the state is suspended, a superposition of multiple possibilities. So if particles only lock in properties when measured, then how does the universe exist when no one is looking? This line of thought is often called observer-dependent reality. Observation might be necessary for the universe to have definite properties. In that view, reality is not entirely standing independently out there, but is co-created through interaction and measurement. This does not necessarily claim the universe disappears when we are not looking, but it undermines the classical idea that the universe is a stable, objective block existing completely independently of us. Instead, reality may be far more flexible depending on interactions between particles, and perhaps the role of the observer, more than we once imagined. Some interpretations, such as Copenhagen, lean in this direction. A particle does not choose a definite state until it is observed. Before that, reality remains indeterminate. Still, other interpretations try to avoid saying observer-dependent, but they cannot fully remove the paradoxes raised by entanglement and non-locality. Many worlds avoiding observer dependence at the price of infinite universes. For example, The many worlds interpretation says that every possible outcome of a quantum measurement truly happens, but in different branches of the universe. When we observe, we do not force the particle to choose a state. We simply find ourselves in one particular branch among countless branches. Each quantum event causes the universe to branch into many versions, each corresponding to a different result. This interpretation avoids saying reality depends on observation, but it comes with a massive consequence: an infinite number of parallel universes. It implies that the universe we experience is only one among countless others, and every possible reality exists. As extreme as it sounds, it is a way to reconcile the weirdness of quantum mechanics with the classical idea of objective reality. Reality remains objective, just no longer singular, Bohmian mechanics keeping objective reality, but accepting a non-local guiding wave. Another interpretation that tries to preserve objective reality is Bohmian mechanics, pilot wave theory. In this view, particles always have definite properties at all times, but their motion is guided by a pilot wave that determines behavior. This wave is non-local, meaning it can influence a particle far away almost instantly. In this way, Bohm allows a deterministic picture in which particles have fixed trajectories. Bohmian mechanics restores the classical feeling of certainty and predictability, but at the cost of accepting a hidden, non-local guiding wave that we do not observe directly. Schrödinger's cat, when superposition touches the meaning of existence. Schrödinger's cat is famous because it exposes a hard-to-believe point of quantum mechanics in the quantum realm. A system can exist in multiple states at once until it is observed. The image of a cat, both alive and dead, sounds like a philosophical puzzle, but it opens the door to deeper questions about the very word exist. In the microscopic world, particles follow rules that feel alien to macroscopic life. Schrödinger's cat pulls that strangeness up to a larger scale, so we can picture it a living creature, trapped in superposition inside a box. Before the box is opened before observation, the cat is treated as both alive and dead, meaning both possibilities exist at once. And if that is true for particles, what happens when we scale the idea up to the universe? In quantum mechanics, being in many states at once does not apply only to a single particle. It can apply to any quantum system, no matter how large or complex. So some physicists propose an even more chilling possibility: the entire universe could be in superposition. That idea is unsettling because it suggests the universe we experience is only one version among countless others, and all possibilities exist simultaneously in some sense. In the multiverse direction, each quantum event could generate another version of reality. In one universe, the cat lives. In another, it dies. In one universe, a particle goes through one slit. In another, it goes through both. Each reality is equally real. What separates them is observation. We experience only one branch, while other branches may exist beyond our reach. Many worlds is extreme, but it can flow naturally from superposition if superposition is real. Then each quantum event may open a new branch. The universe becomes like a branching tree of possibilities. Each observation is a fork. And that brings us back to the question of existence. What does it mean for something to exist if it can exist in many states at once? If the universe itself is in superposition, then the word exist becomes slippery. Are all versions equally real, or is there something special about the version we see? And if observation is what makes superposition collapse, what makes one version become selected, then does reality depend on us? Parallel universes versus non-existence. Where is the difference? The idea of parallel universes is compelling because it breaks the habit of thinking there is only one reality. At its core, Many Worlds says each possible outcome of a quantum event creates a branch universe. Universes exist in parallel, each a different version of reality. In that interpretation, when you turn left or right, the universe branches. In one branch you turn left, in another you turn right. Both exist, but in different realities. This picture offers a clean solution to superposition. A particle seems to be in many states at once because all those states are truly real, just not inside the same universe. Each possibility is realized in its own universe, leading to endless proliferation of worlds. But then another question appears. How does that fit with the possibility that no universe, including ours, really exists the way we think? Some views, influenced by philosophy, suggest an even more unsettling possibility. Reality may be an illusion. In this direction, what we experience as reality could be a projection of the mind or a structure created by the act of observation itself. There is no single real universe independently out there, only appearances that arise when we interact with the quantum world. So is many worlds more reasonable than the idea that no universe truly exists? Both break intuition, but in opposite directions. Many worlds says reality is larger than imagination, filled with universes we cannot touch. Every possibility is real, just in different worlds. Reality as illusion says no possibility is deeply real. What we call reality is only a surface appearance, a shadow part. Many worlds gives a strange kind of comfort, even if bizarre. It preserves the sense that reality runs by some rules. Universes still follow physical laws, only differing in how outcomes unfold. Each universe exists independently of us, objective in its own way. By contrast, the reality is an illusion. Idea is more frightening. It suggests our sense of living in a solid, stable world may be a convenient story. If the universe is an illusion, then what we see and touch is not the essence but an appearance. The real universe, if it exists, remains beyond observation. In many worlds, the observer is relatively passive. Observation merely reveals which branch we experience. All branches exist. The observer does not decide which reality becomes real. In the reality as illusion view, the observer plays a more active role. Reality depends on observation. The universe we experience is not necessarily an objective entity, but the result of interaction between mind and the quantum world. Without an observer, there is no reality in the familiar sense, only a cloud of possibilities floating, never forced to collapse into something called real. And that thought returns us to the uncomfortable question: does the universe exist when no one is looking? Is there an independent world outside perception? Or is reality only a projection screen produced by observation? Quantum decoherence. How does reality freeze? Quantum decoherence is one of the most important links in quantum mechanics that helps connect strange particle-level behavior with the stable world we live in. It provides a framework for understanding how countless possibilities in a quantum system become one version of reality that we can observe. At its core, decoherence is the process by which a quantum system gradually loses its quantum signatures and begins to behave more classically, that is, it increasingly follows the familiar kinds of behavior we see every day. In quantum mechanics, a particle can be in superposition, spinning in two directions at once, or present in two positions simultaneously, at least in the mathematical description. But in everyday life, we never directly see an object both here and there. We only see one outcome. So what makes reality solidify from the fluidity of quantum possibilities into the definite world we experience? Decoherence answers along these lines. When a quantum system interacts with its environment, it becomes entangled with that environment. This means each possible state of the quantum system will drag along different corresponding states of the environment. Over time, those interactions break the coherence of the superposition. The system no longer behaves as if it is in many states at once. Instead, it appears as if it has tilted toward one specific state, the state we actually observe. Imagine a simple example: an electron could be in two places at the same time. Before it touches the environment, it is in superposition, meaning it is both at position A and at position B. But the moment the electron interacts with anything around it, a photon, an atom, even air molecules, it begins to become entangled with them. The superposed branches of the electron become attached to different environmental conditions. The more interactions, the more the phase coherence dissolves, and observing the electron in both positions becomes impossible. Eventually, the electron looks as if it is in one definite position. That is decoherence at work. Many possibilities are blurred into a world we can observe. One way to understand decoherence is to treat the environment as measuring the quantum system without humans directly seeing the process. However, the environment does not necessarily choose a single outcome for us. What it does is make the system lose the ability to display superposition in a way we can observe. Thanks to that, we understand why, in daily life, objects do not appear as if they are superposed in many positions or many states. Decoherence almost hides the weirdness of quantum mechanics from our eyes, so we only see a stable classical reality. But here is the crucial distinction. Decoherence is not the same as wave function collapse in the strong sense. In quantum mechanics, decoherence and wave function collapse are often mentioned together, but they are not one. Decoherence, a physical process that occurs when a system interacts with the environment. Wave function collapse, a concept describing how quantum possibilities reduce to one observable result. In short, decoherence explains why we do not see superposition in daily life. But it does not fully answer the question, why does a particular specific result appear when a measurement occurs? And this is where interpretations of quantum mechanics enter, such as many worlds or Copenhagen. According to many worlds, decoherence causes possibilities to branch into separate realities. Every result happens, but in different branches. In Copenhagen, decoherence is seen as part of the process, leading to one single outcome being observed when measurement occurs. If there were no decoherence, everyday life would be filled with quantum anomalies. Imagine sitting on a chair that is in many places, or holding a cup that is both empty and full. Decoherence is one important reason why paradoxes like that do not invade macroscopic experience. But what if decoherence does not happen in the right way? Or if quantum effects begin to play a clear role at larger scales? Much of this remains theoretical, but it suggests fascinating consequences about the nature of reality. Some researchers speculate that systems extremely well isolated from the environment could retain quantum coherence longer. In that case, they could maintain superposition and behave contrary to classical intuition. A representative example is the quantum computer. Quantum computers rely on qubits, systems that can exist in superpositions of many states to compute. But to do that, they must preserve the quantum coherence of qubits long enough. This is extremely fragile. Even a tiny interaction with the environment can cause a qubit to decohere, the superposition to vanish, and the computation to fail. Therefore, decoherence is one of the biggest challenges in building reliable quantum computers, because it constantly threatens to break the very mechanism that gives quantum computers their power. In biology, there is also a line of research asking whether quantum coherence might contribute to certain living processes. There are hypotheses that quantum effects could be related to mechanisms such as photosynthesis, where plants convert light into energy with astonishing efficiency. The idea is quantum coherence could allow energy to try many pathways at once, thereby optimizing the route. Although this field still involves much speculation, it opens the possibility that quantum mechanics may touch the macroscopic world more than we currently understand. Does quantum information define reality? The deeper we go into the strange quantum domain, one notion begins to emerge, perhaps at the deepest layer. The universe is not defined by matter, but by quantum information. If that is true, what we call objects are merely expressions of a deeper informational structure. Quantum information differs from the classical information we encounter every day. The classical world uses bits 0 or 1. Traditional computers process data in that binary form. But the quantum world uses qubits, which can be in a superposition of both 0 and 1 simultaneously, just as particles can be in many states. Therefore, quantum information has properties that do not match everyday intuition. One key property: quantum information cannot be copied in the way classical information can. That is the no-cloning theorem. You cannot create a perfect copy of an unknown quantum state. While classical information can be duplicated freely without loss, quantum information carries a special fragility and indeterminacy, and from here a strong inference arises. If we cannot copy a quantum state the way we copy classical data, then information in the quantum realm seems to play a more fundamental role in shaping what we call reality. In this view, particles, atoms, even larger objects are not the final bricks. They are the result of deeper informational processes that produce the physical world we observe. This idea also suggests a bold image: the universe as a gigantic quantum computer, processing information at a layer we do not directly sense. The physical world, in a sense, is the output of that processing. In this context, quantum entanglement is a prime example. The flow of correlation does not respect space-time boundaries. The connection exists at the level of information, suggesting that physical objects may be secondary compared to the information they carry. If information is fundamental, then the space-time framework we use to understand the universe may not be the deepest layer. Space and time may emerge from quantum informational structure just as physical objects emerge. This shift in thinking leads directly to a hot research domain, black holes. For many years, people thought that matter falling into a black hole carries information and that information disappears. But quantum mechanics says information cannot be destroyed, creating the black hole information paradox. To resolve the paradox, researchers return to the question, how is quantum information kept in a black hole? One prominent idea is information is not destroyed, but stored on the event horizon, the two-dimensional boundary of the black hole. This is the doorway to the holographic principle. All the information of the three-dimensional space inside could be encoded on a two-dimensional surface. If the universe also operates by a similar principle, then what we experience as a three-dimensional reality may be only a projection of quantum information stored on a structure with fewer dimensions. The objects in space we interact with could be like a hologram, manifestations of an informational structure lying deeper underneath. And this idea is not only speculation. There are efforts to test it, including searching for whether space has a pixel-like structure, like a digital image made of pixels. If space is truly made of discrete units of information, that would be a strong sign that the universe's foundation is informational. The holographic principle is the universe only a 2D projection. The holographic principle, connected to theoretical physics and cosmology, challenges our deepest intuition by saying that the three-dimensional world we see may be only a hologram-like illusion. This idea was developed in part by the Dutch physicist Gerard Hooft, and later expanded by Leonard Susskind. They proposed information about matter falling into a black hole does not vanish, but is encoded on the event horizon, the two-dimensional surface surrounding the black hole. Through that encoding mechanism, information can be preserved, even if the black hole ultimately evaporates. In that sense, the event horizon resembles a holographic film, storing information about what is inside in a two-dimensional form. At first, the principle aimed to resolve the black hole information paradox, but its broader implication is even more staggering if it applies to black holes. Perhaps it also applies to the entire universe. Then, a suggestion appears: everything in the universe, including space-time, could be described by information stored on a very distant two-dimensional boundary, possibly at the edge of the universe. In this view, the three-dimensional world, with depth and volume, is only a projection of information encoded on a plane, like a hologram, producing a three-dimensional feeling from a two-dimensional film. The objects we touch, the distances we measure, and even the flow of time may all be part of a gigantic projection. The holographic principle is supported by many branches of theoretical physics, especially in string theory, where it helps provide a framework for understanding gravity in a universe with more than 3 spatial dimensions. A famous application appears in the study of anti-de Sitter space, where the holographic principle becomes clear through the AD-S-CFT correspondence, a relationship between a gravity theory in a higher dimensional space and a quantum field theory on a lower dimensional boundary. This correspondence has brought many insights into black holes and quantum gravity, and has clarified how the holographic principle might operate. Virtual particles. How real are the building blocks of matter? Another puzzling idea in the quantum world is the virtual particle. They are not like stable particles such as electrons or protons. Virtual particles are fleeting entities, continuously appearing and disappearing in the quantum vacuum. And that throws out the question, what is the smallest component of matter, ultimately, and is even that foundational layer as real as we think? In what is called the quantum vacuum, often misunderstood as empty, there is actually no emptiness. According to quantum field theory, the vacuum is always active. Fields fluctuate throughout space, even where there is no matter. From those fluctuations, virtual particles can flash into existence and disappear almost immediately. They do not last long enough for us to observe directly. But the strange thing is that their fleeting existence still leaves measurable effects. In the 1940s, the Dutch physicist Hendrik Casimir proposed that if you place two uncharged metal plates extremely close together in a vacuum, an attractive force will appear between them due to the influence of virtual particles. The Casimir effect was later observed experimentally, a sign that vacuum fluctuations can exert physical force on objects. Even so, virtual particles are not considered real in the same sense as electrons or protons. They exist for extremely short times, born from fluctuations and quickly cancelling out. We can imagine virtual particles as temporary disturbances in the background of quantum fields, ripples that do not have time to solidify into stable matter. What is thought-provoking is virtual particles play an essential role in fundamental forces. In quantum electrodynamics, QED, electromagnetic interaction is described as the exchange of virtual photons. We do not see virtual photons, but they are an indispensable part of the interaction. In quantum chromodynamics, QCD, the strong force that holds the nucleus together is described through the exchange of virtual gluons between quarks, binding them to form protons and neutrons. Without this exchange, the structure of matter as we know it might not exist, and so a subtle but deep paradox appears. The forces that shape the universe rely on entities that make us question what real means. If virtual particles are not real in the traditional sense but still affect experimental outcomes, what does that say about the nature of reality? Are they merely mathematical tools? Or are they revealing that the fabric of the universe is woven from temporary, hard-to-define entities? It also leads to another question about emptiness. If the vacuum is full of fluctuations and the potential to generate virtual particles, is it correct to call the vacuum empty? And if the building blocks of matter can rise up and dissolve in the quantum vacuum, reality may not be as solid as we feel it to be. What we call real may be only a temporary order of quantum information and underlying fluctuations. Black holes and the information paradox, a crisis of reality. Black holes are always both fascinating and frightening. Gravity strong enough to hold back everything that crosses the event horizon, including light. But one question keeps returning. Where does the information that falls into a black hole go? The black hole information paradox was born from that question and became a crisis for how we understand reality. In classical intuition, matter falling into a black hole disappears from the outside world. But in the 1970s, Stephen Hawking proposed that black holes are not completely black. They emit Hawking radiation and over time can evaporate and vanish. If a black hole disappears, then where does the information about everything that ever fell into it go in physics? Information is central, the state of a system position. Motion, properties is information. Quantum mechanics emphasizes a principle: information cannot be destroyed. But if a black hole evaporates completely, information seems to disappear, contradicting that principle. The problem becomes stark. Either black holes destroy information, a direct collision with quantum mechanics, or our understanding of black holes and the nature of space-time is missing something deeper. Imagine you throw a book into a black hole. The book contains enormous information: atomic structure, letters on the pages, the chemistry of ink. When it crosses the event horizon, it vanishes from the outside world. But is the book's information erased from existence? Classical physics can easily answer yes. Quantum mechanics does not allow that conclusion. Hawking radiation makes the story more tangled. The black hole shrinks, emits radiation, and then disappears. If the radiation carries no information, then when the black hole fully evaporates, the information seems completely lost, violating information conservation. So the paradox becomes a hotspot, where general relativity describing black holes in space-time and quantum mechanics governing particles and information collide head-on. Many solutions have been proposed, and every solution demands that the mind stretch. One idea: information is actually encoded in Hawking radiation, but it is scrambled so violently that it is nearly impossible to decode. Another possibility: information is not destroyed, but stored in some hidden way. And that idea connects directly to the holographic principle: three-dimensional information inside is encoded on a two-dimensional boundary. thereby preserving it even when the black hole evaporates. Then there are even more far-reaching hypotheses. A black hole might be a doorway to another universe, a kind of cosmic tunnel that sends information into a different region of space-time. In that scenario, information is not destroyed. It is only displaced, slipping into a universe or a dimension beyond our ability to detect. Some even imagine a white hole, an opposite counterpart of a black hole that continuously spits out mass, light, energy, and information, and into which nothing can enter or cross its horizon in the reverse direction. The black hole information paradox is so serious that it can shake the foundations of the two most successful theories. Humans have quantum mechanics and general relativity. The fact that they cannot both stand still in the face of the black hole problem suggests that we are missing a core piece of the universe, and it pulls in a sharp philosophical question: if information can be lost, do the objects and events that fall into a black hole cease to exist? In some sense, is a black hole a boundary not only for objects, but for reality itself? And if reality is tightly tied to the ability to preserve information, does reality depend on whether information is retained? The role of consciousness: does the universe need an observer to take shape? The question of whether consciousness participates in defining the universe has ignited a major debate between science and philosophy. The root of the debate lies in a familiar implication of quantum mechanics. Particles seem to exist in many states until they are observed. Before observation, they have no definite position or state. Only when there is a measuring interaction do they collapse into a particular state. If observation is what formats reality, can the universe exist without observers? The observer effect emphasizes that observing a quantum system can change the system in a fundamental way. For example, in the double-slit experiment, electrons fired through two slits create an interference pattern like waves if we do not track their path. But when we observe, electrons behave like particles going through this slit or that slit, and the interference pattern disappears. It is as if the act of looking forces the system to choose, turning wave-like behavior into particle-like behavior. Without observation, the system is indeterminate, a bundle of possibilities. When observation appears, those possibilities collapse into a result. If we scale this up to the entire universe, the question becomes sharper: is the universe independent of us? Or does it need observers, conscious beings, to shape itself into a definite reality? If collapsing quantum possibilities into a specific reality requires observation, is consciousness a foundational component of reality's structure? The Copenhagen interpretation associated with Niels Bohr and Werner Heisenberg suggests that a particle has no definite state until it is measured. In that view, the act of measurement, observation, brings the particle into a particular state, implying that the physical universe might not have a fully defined reality without intervention by observers. Some go even further, claiming that consciousness is the key to existence. Reality is not fully objective, but subjective, shaped by perception. In that view, the universe remains in a potential state, full of quantum possibilities, until consciousness interacts and closes those possibilities into the reality we experience. But this position faces strong objections. Many researchers argue that saying consciousness creates reality misunderstands the role of observation in quantum mechanics. Observation does not necessarily require a conscious observer. It may only require a physical interaction that makes the system definite. For example, a photon interacting with an electron can be considered as observing the electron, pulling it from superposition into a specific state. In this sense, observation could simply be physical interaction, not an act of consciousness. Wigner's friend: can two observers live in two realities? Wigner's friend is a provocative thought experiment. Can different observers experience different realities? It rests on a quantum foundation. Observation is not passive. It is an interaction that can make a system collapse from superposition into an outcome. Wigner pushes the question further: can two observers disagree about what is real? Imagine a quantum system, a particle in superposition, carrying many states at once. Wigner's friend is inside a lab, directly measuring the system. Wigner is outside, not yet knowing the result. From the friend's point of view, the measurement has collapsed the system into a clear outcome. For them, the superposition is over. The system has chosen a state. But from Wigner's outside point of view, until he opens the door and interacts with the whole lab system, the quantum state of the entire particle, plus friend, plus apparatus, can still be described as a superposition, and the paradox appears. Inside the lab, the friend lives in a reality that has taken shape. Outside the lab, Wigner still describes everything as undefined, with many outcomes coexisting. So who is right? Does the friend's experience decide what is real? Or is Wigner's broader description also valid? In some interpretations, this leads to the idea that there is no single universal reality shared by everyone, but that each observer constructs a version of reality based on the information they obtain through interaction with quantum systems. Its philosophical consequences spill beyond physics into perception, truth, and the role of consciousness. To approach ideas like Wigner's friend, physicists have designed quantum experiments to test how different observers might record different outcomes. Although there is no final conclusion yet, one thing is increasingly clear. The relationship between observers and the observed universe is more complex than we once believed. Simulation theory is reality, a computational process. Another attempt to reorganize the strangeness of reality is simulation theory. It proposes that reality might be an extremely sophisticated simulation, perhaps running on a super-advanced quantum computer. In this view, the universe could be a computational process, operating through interactions of information. And seen this way, quantum mechanics with indeterminacy, superposition, and entanglement suddenly looks compatible with the logic of a world that is computed and updated through interaction. Particle indeterminacy, the fact that states only lock in when observed. Entanglement could be viewed as signs of a virtual reality. Information is processed and updated based on interactions occurring within the simulation. If reality is a simulation, that could explain why superposition and entanglement are so hard to fit into a classical frame. A simulation does not have to behave the way we expect the real world to behave. It could run on different rules, and those rules might be revealed only partially through quantum phenomena. Key idea: computational limits and rendering. A core point in simulation theory is resource limitation. Just as a video game only renders detail when the player looks in a direction, quantum particles might only lock in a state when observed. That would save resources, no need to compute every detail until that detail becomes relevant. The collapse from superposition into a definite state can look like a reflection of that logic, as if the universe does not need to compute a state until someone looks. In a simulated universe, entanglement might be a layer of underlying code. Two particles are linked by a shared update rule, keeping their states synchronized even when far apart. To us, that looks like a mysterious connection beyond classical limits. In a simulation, it is simply the program updating two objects under the same instruction. This helps visualize why non-locality appears. A change in one particle comes with a change in the other, regardless of distance. The big problem: extremely hard to test. The biggest challenge in proving simulation theory is that if it is true, it would be extremely hard to detect. Like a character inside a game rarely has a way to know they are inside a game. We may lack the viewpoint needed to see the boundary of the simulation. Still, some argue the universe might reveal clues of limitations like pixelation when you zoom in on a digital image. One commonly mentioned hint is discreteness of space and time at the smallest scales. As quantum ideas suggest, like a digital image made of pixels, the universe might be built from discrete units, Planck length and Planck time, implying a kind of grid that behaves like computational substrate. Another sign: the fine-tuning problem in cosmology. Fundamental constants, the strength of gravity, the electron charge, the cosmological constant, appear finely tuned to allow complex structure and life. In a simulation context, such tuning could be intentional, a design to create a stable environment. And then the chilling question appears: why would the programmers run the simulation? Experiment curiosity, or some other purpose? Another disturbing thought: If we are in a simulation, it could be altered or shut down at any time, like a game being paused, reset, or deleted. If the simulation ends, would we notice, or would we simply cease to exist? Nick Bostrom's simulation argument, a probability problem. Many people do not only say simulation is possible, but that it may be high probability. Nick Bostrom's argument frames it as probability, based on assumptions about the future of civilization and technological capacity. If advanced civilizations reach a stage where they can create extremely detailed simulations, so detailed that beings inside have consciousness, then the probability that we live in base reality rather than a simulation would drop sharply. Bostrom presents three possibilities, and he argues at least one must be true. 1. Civilizations never reach the ability to create advanced simulations. Even if they do, they choose not to. San. They create many simulations, and then the probability that we are in base reality rather than one of countless simulations becomes very low. The logic is simple. If there are countless simulations, and each simulation contains beings who do not know they are simulated, we have no special reason to believe we are in the real one. By probability, we might simply be one among many simulations running controlled by a civilization far beyond us. Multiverse and the Matrix, could they be one? The multiverse and the simulation hypothesis are two ideas that push the boundaries of how we understand reality. They seem to come from different regions of thought, but they may share a surprising common ground. Could they be describing the same thing just from different angles? Think of nested simulations. If we live in a simulation, then the beings who created our simulation might also live in another simulation. Then layers of reality stack on top of one another, each layer being a product of the one above. No clear boundary between real and simulated. If each quantum event creates a branching universe, those branches could also be seen as different versions of a simulated reality. The multiverse then resembles a vast simulation network, continually generating new realities based on quantum events, like a game generating new environments as the player progresses. In that sense, many worlds and simulation could be two sides of the same coin. Both describe a system where many realities coexist and are shaped by underlying processes. In a sufficiently advanced simulation, running many versions of reality in parallel is not hard to imagine. Each version carries its own parameters and outcomes. They could be independent, or interact in subtle ways, similar to how parallel universes are described in multiverse stories. From this viewpoint, multiverse and simulation do not only touch, they may be describing the same reality, simply approached differently. And then a question arises: can a simulated multiverse be distinguished from a real multiverse? If we live in a simulation, and that simulation contains many universes, how could we know whether those universes are real or just the next layer of simulation? Practically, from the inside, there may be no difference. Each universe would feel equally real. The inhabitants of each universe, whether they know or do not know they are in a simulation, would still experience their lives the way we experience ours. In that sense, the boundary between a real multiverse and a simulated multiverse may become not so important. Quantum simulation have we already started imitating reality. Today, quantum simulation has become a key piece of modern science, especially in quantum physics and computation. Simulating reality at the quantum level is pushing the boundary of human understanding of the universe, and at the same time hinting at the possibility that one day we could create our own simulated realities. Quantum simulation uses quantum principles to model extremely complex systems that classical computers struggle to handle. It has become a bridge between theory and application, showing that the idea of simulated reality is not only on paper but is being tested in laboratories. Quantum simulation can reproduce natural processes with an accuracy that traditional simulation cannot reach. Classical computers are based on binary logic 0-1, very powerful for many tasks, but they often fail when modeling a quantum system because a quantum system is not locked into either this or that. In the quantum world, particles can be in superposition, can be entangled, and can display behaviors that contradict classical intuition. Quantum simulation uses the power of quantum computers to imitate that language directly from the smallest particles to larger systems such as molecules or complex interacting environments. By processing information in a way that reflects the probabilistic nature of quantum mechanics, quantum simulation touches a deeper foundational layer of reality. A key strength of quantum computation is the ability to handle many component interacting systems. In classical simulation, the number of computations often explodes exponentially as variables increase, quickly making the problem infeasible. Quantum computers are different thanks to superposition. Qubits can exist in many states at once, allowing exploration of many possibilities simultaneously, almost a natural kind of parallelism. That helps quantum computers simulate far more complex systems than classical computers can. A representative example: chemistry, medicine, materials, energy. A flagship application of quantum simulation is chemistry. Chemical reactions are inherently quantum processes, involving electron and atomic interactions under quantum rules. Understanding reactions at the fundamental level is extremely hard for classical computers, because the number of possible states grows explosively. But with quantum simulation, scientists can model molecules and their interactions at the quantum level with higher accuracy. This allows better prediction of reactions, opening the door to breakthroughs in drug discovery, materials science, and renewable energy. Developing new materials also depends strongly on how atoms and molecules interact. The search for superconductors, materials that conduct electricity with zero resistance, relies heavily on quantum simulation. By modeling quantum interactions in materials, researchers hope to find superconductors that work at higher temperatures, potentially transforming how energy is transmitted and stored. Similarly, quantum simulation is used to study exotic states of matter, such as quantum spin liquids and topological insulators, systems with potential applications in quantum computing and other advanced technologies. Going where we cannot measure: black holes, the early universe, extreme conditions. Quantum simulation also allows exploration of phenomena that are almost impossible to study directly. Particle behavior in extreme environments, for example inside black holes, or in the early universe, places where the laws of physics in everyday intuition begin to fall apart. Experimental data in those regions is extremely rare, even nearly impossible to obtain, so quantum simulation creates a kind of virtual space we can enter, adjust parameters, and extract clues that would otherwise remain out of reach. Not only can we simulate our universe, we can also explore scenarios where the laws of nature are completely different. That lets us imagine what other universes might look like: different forces, different numbers of dimensions, different forms of matter. In our universe, there are 4 fundamental forces: gravity, electromagnetism, and the 2 nuclear forces, strong and weak. They shape everything from atoms to galaxies. But what if a universe had only 2 forces, or 10? Quantum simulation lets us play with those variables, explore a world without gravity, or one where gravity dominates, a world where light behaves strangely, or a world where time flows differently. And sometimes, breaking the rules in simulation brings back new insight about the real rules. For example, simulating a universe without gravity might sharpen intuition about why gravity is weaker than other forces. Or simulating a different space-time geometry might offer clues about the nature of dark energy. In that sense, quantum simulation of alternative realities becomes a powerful tool for scientific discovery, opening a new angle on old questions as vast as the sky. Looking further ahead, using quantum simulation is moving us closer to the possibility of creating simulated realities. Right now, we still cannot simulate an entire universe, and we certainly cannot simulate conscious beings. But the underlying technology is being developed right now. As quantum computing advances, the complexity and scale of simulations will grow. We can imagine a day when simulations become so detailed that they are hard to distinguish from the real. In the future, quantum simulation may not stop at physics, but reach into consciousness and artificial intelligence. If a quantum computer can simulate complex systems, could it simulate the human mind? Could it create artificial intelligences that experience a version of reality of their own, even believing they are conscious? And so, an ethical question opens. If a simulation can reproduce the processes of the brain, is that simulated mind any less real than our mind? Digital physics is the universe, a piece of code. If, at the deepest layer, the universe operates like a gigantic computational system, then instead of being made of continuous waves or solid matter, everything might be built from discrete units of information, like the way computers process data using binary code. This direction of thought, often called digital physics, attracts some scientists and philosophers because it offers a framework to interpret the strange behavior of quantum particles and the feeling that the universe is hard to predict. If we see the universe as digitized, we can imagine reality as a code base, a set of rules and algorithms governing all operations. Then solid matter may not be solid in the way we think. It is like information wearing a physical form, not because it is inherently dense, but because the underlying rules force it to display that way. Like an image on a screen that looks solid, but is really pixels controlled by software. A key idea in digital physics is the universe might be divisible down to the smallest possible units. Call them bits of the universe. Just as bits make data, these units might be tiny quanta of energy, space, or time put together. They form the substrate of everything. In that view, the universe cannot be divided infinitely. There is a smallest level. At that level, the universe behaves like a vast computational network, processing fundamental bits of information. If that is true, the universe resembles a giant simulation. The laws of physics are the laws of the program. Everything follows that internal logic, like a game, with rules that permit and forbid. This also suggests a way to understand quantum jumps in a digitized system. Things do not have to be smooth. They can be processed in discrete steps, like a computer calculating in ticks. Some supporters of digital physics point out that the universe seems to have finite limits. For example, the speed of light is a universal constant. Nothing can go faster, placing a foundational limit on how information can move. And at extremely small scales, space seems to behave strangely, as if it is not a smooth, continuous sheet, but more like a pixelated surface. This matches the intuition of a computational grid. The continuity of space-time may be an illusion emerging from a network of tiny units. Digital physics also touches time. In classical physics, time is continuous, but in a digital universe, time might consist of discrete steps like frames of a film or the tick of a computer clock. Each tick is a moment, and the universe moves from one moment to the next in a stepwise process. If so, time also has a smallest unit. From here, an ambition is born. Perhaps one day we will crack the code of the universe, find the underlying algorithm that governs everything. That would be the highest aim of physics, not only describing how the universe operates, but understanding the deeper logic that generates everything we see. The quantum Zeno effect. Can observation freeze reality? The quantum Zeno effect is a phenomenon that distorts intuition about time and change. In everyday life, we believe things evolve over time. You watch a pot of water, and it boils. But in the quantum world, continuous observation can produce something strange if you measure a system very frequently. At extremely short time intervals, you can prevent it from evolving, as if it is frozen in its current state. The name Zeno recalls the ancient Greek philosopher famous for paradoxes of motion. The arrow paradox says that at any instant, an arrow in flight is still at a fixed position. If time is only a collection of frozen instants, motion seems impossible. In daily life, the arrow still flies, but in quantum mechanics, that logic seems to be partly true. Frequent observation can block change. The Zeno effect is closely related to wave function collapse. A system remains in superposition until measured. When measured, it takes on a definite state. If you measure too often, you repeatedly force the system to collapse back into a state, not giving it time to shift into another state, like pressing pause over and over. For example, an atom in an excited state is about to decay to a lower level and emit a photon. Normally it will decay, but if you continuously observe its state, The atom can be stuck in the excited state, not decaying as usual. An experiment illustrating the Zeno effect was carried out in the 1990s with cold ions. When measurements were applied frequently, evolution was suppressed exactly as theory predicted. The ions were kept in the initial state longer, as if locked. The time problem is time truly fundamental. Time is one of the greatest mysteries. Experience gives us the feeling that it flows continuously in one direction. But when we look deeper into the laws, especially through the quantum lens, time becomes less certain. In Einstein's picture, time is not absolute. It changes with speed and with gravitational field. Time can stretch or contract. Time dilation. Someone moving very fast or near an extremely massive object like a black hole experiences time passing more slowly. As strange as it is, relativity still treats time as real, a dimension that can be bent and stretched, but still exists. Quantum mechanics pushes the question further. When particles exist as probabilities, when events are not locked in until measurement, we begin to ask, is time as we understand it truly foundational? In many quantum equations, time appears as a variable, but it often feels like it is inserted from outside into the system. Unlike quantities tightly tied to internal measurement, so there are lines of thought suggesting that time is not a basic property, but something that emerges from other processes. One equation that touches this idea directly is the Wheeler-DeWitt equation, which tries to describe the universe as a whole in a quantum framework. The shocking part, the equation seems not to need time, it is timeless. From this comes speculation that the time we experience may be only a phenomenon emerging from how we interact with the universe, rather than a foundational property of the universe itself. If the universe can be indeterminate, in superposition until measured, what does time say about that? One possibility is time is a product of how we perceive and observe. In this view, time may become meaningful only when we interact with the universe, just as a particle's state becomes definite only when measured. No observer, no measurement, perhaps no time as we normally feel it, only a universe of possibilities, hanging suspended, waiting for something to lock it into reality. But there is another possibility: time still exists at the quantum level, only in a form that classical intuition cannot grasp. There are proposals that time could be quantized. It does not flow continuously like a river, but arrives in discrete pieces like frames of a film. At the deepest level, time ticks in extremely small, indivisible units. Events do not slide smoothly from one moment to the next, but jump in steps. Our brain seems programmed to feel time as a seamless flow, but that feeling may not reflect how time truly operates. It is very possible that time passing is a functional illusion, a way the nervous system creates order from the world. If the foundation of the universe is indeterminate, more probability than certainty, then time might be a product of our effort to turn that indeterminacy into a story with a before and after. In this sense, time may be like temperature. Temperature is not a fundamental property of each single particle. It emerges from the collective behavior of countless interacting particles. Similarly, time may emerge from the collective behavior of quantum systems as they interact with the environment and with observers. No observer, no measurement, perhaps no time in the familiar sense, only a superposed universe. In a non-time state of potentialities, Max Tegmark's mathematical universe is reality-only numbers. Max Tegmark, a Swedish-American physicist, proposed a bold hypothesis: the universe is not merely described by mathematics, the universe is mathematics. The mathematical universe hypothesis pushes the idea of description to the extreme. Everything we call real, from distant galaxies to atoms in our bodies, is ultimately a mathematical structure. For Tegmark, the physical universe is nothing more than an abstract mathematical object. This idea reverses a familiar assumption: mathematics is only a tool to describe the world. In physics, we use equations to predict particles, forces, energy. We tend to think those mathematical structures describe an external world that exists independently of math. But Tegmark argues the opposite: the mathematical structure is the foundation, and the reality we perceive is only the surface layer. At the core of the hypothesis is the notion that all existence can be reduced to numbers and the relations between them. Physical laws, from the motion of galaxies to particle behavior, can be written as mathematics. Einstein's equations are not only a way to describe mass energy, they resemble a statement about the deep logic of the universe. For Tegmark, those equations do not only describe the world, they are the world. The universe does not simply follow mathematics. The universe is a mathematical structure. In everyday life, physical objects feel most real because we see and touch them. A tree seems solid, but for Tegmark, the tree is a set of mathematical properties: shape, size, color. Everything can be reduced to geometry, numbers, equations. The physical tree is just how the underlying mathematical structure appears. Tegmark goes even further. If the universe is mathematical in nature, then other mathematical structures could also exist as universes in the full sense. Each valid mathematical structure could correspond to a different universe, with different laws, perhaps completely unrecognizable to us. In daily life, we sharply separate the real objects from the abstract numbers. This hypothesis says that boundary is an illusion. The number 2 could be as real as a chair, just a different kind of mathematical structure. If the foundation is mathematics, then what we call reality is only how we interpret those structures. When you look at a tree, you see color, texture, solidity. But for Tegmark, what you are really reading is a mathematical structure, and the brain, also a mathematical structure, translates it into an experience that fits you. One appealing aspect of this hypothesis is that it suggests a unified framework in modern physics. There are many models describing different parts of the universe, from quantum mechanics to relativity, but they do not always fit smoothly. Tegmark suggests these may be different expressions of the same underlying mathematical structure. Still, it is highly controversial. The biggest criticism: it is very hard to test. Science usually relies on observation and repeatable experiments. If the universe only exists as an abstract structure, how do we test it? Many consider the hypothesis closer to philosophy than science because it lacks specific experimental predictions. It also brings an uncomfortable question about the nature of mathematics. If the universe is a mathematical structure, where do such structures come from? Are they created by the universe, or do they exist independently? If independently, then where do they exist? Free will in a universe that might not exist. When we touch the foundation of the universe, the question of free will often appears. If everything lies in a predetermined system, or more radically, if the universe does not exist the way we think, do our choices still have meaning? In daily life, we are used to believing we can decide what to eat, where to go, how to live. But when viewed through physics, the story becomes more tangled. One challenge comes from determinism. In classical physics, the universe is like a clockwork machine. If we knew exactly the state of every particle at one moment, in theory we could predict the future. That view leaves almost no room for free will if the present is locked by the past. Where can freedom be? Quantum mechanics introduces an element that cannot be predicted with certainty. Microscopic behavior is described only by probabilities. This seems to open the door to freedom because the future is not completely nailed down. But randomness is not freedom. Randomness is something we do not control. If actions are driven by random quantum events, they may be unpredictable but not necessarily free in the sense we want. And the paradox appears: neither complete determinism nor pure randomness neatly resolves free will. In the simulation hypothesis, the issue becomes even more precarious. If we live inside an extremely sophisticated program, our actions might be nothing more than responses to code, like a game character who feels as if they are choosing, but is actually governed by underlying logic. Nick Bostrom's simulation argument intensifies that feeling. If a civilization advanced enough can run universe simulations, and they run many of them, then the probability that we live in base reality becomes small. In that context, it becomes difficult to preserve free will as something solid in the old sense. But what if the universe, or the way we perceive the universe, does not exist in the classical way? If reality is more like a set of probabilities than an objective external world, Where does free will even sit? Some people say if consciousness helps collapse possibilities into outcomes, then our choices might influence how reality appears. But even then, it still is not quite free will in the traditional sense, because in quantum mechanics, the observer does not choose the outcome. They only participate in the measurement. Can physics explain consciousness in a non-material universe? Consciousness, the feeling of being oneself, is both private and unmistakable. It does not seem to fit neatly into the way classical physics describes the world. We can measure brain activity with MRI, but that does not answer. Why does subjective experience arise? One idea is consciousness may be related to quantum processes in the brain. A well-known theory is orchestrated objective reduction, proposed by Roger Penrose and Stuart Hameroff. In this view, consciousness emerges from quantum processes occurring in microtubules, tiny structures in the cell's cytoskeleton. Penrose and Hameroff suggest that microtubules might sustain quantum states and then collapse through some mechanism. Those collapses form conscious experience. Consciousness, in their view, is not merely a byproduct of complex neural networks, but is tied to the deep structure of the universe. This intersects with ideas that treat consciousness as fundamental, such as panpsychism. Consciousness is a universal quality, present from the smallest particles to the largest structures, and human consciousness is just one expression. Some other interpretations even suggest that consciousness and the universe are not separate two sides of the same coin. There is the idea of quantum monism. There is only one underlying entity from which both matter and mind arise. Consciousness and physical reality are two expressions of the same deep quantum process. Of course, the objections are strong. The brain is warm, wet, and noisy, not an ideal place to maintain delicate quantum coherence. Quantum effects often require low temperatures and isolation, which is hard to imagine in the human brain. Still, research into quantum effects in biology continues. There are indications that quantum coherence may contribute to certain functions such as photosynthesis. If living systems can maintain quantum effects under some conditions, a natural question arises: could the brain somehow also do so? In the end, is this physics, philosophy, or fiction? Physics, at its core, is an effort to understand how the universe works. For centuries, it has delivered beautiful answers from planetary orbits to the forces that hold atoms together. But the deeper we go into the quantum realm, the more the answers become dizzying. The closer we get to the foundation, the more the universe seems to resist simple explanations. Many ideas here: multiverses, simulation, observer-dependent reality sound so strange that they resemble fiction. And that raises the question, is physics moving closer to philosophy? Because many of the problems we touch now, what is existence? What is consciousness? Is reality objective? Sound more like a philosophical dialogue than a laboratory problem. Traditional science relies on verification, repeatable experiments, clear observation. But many modern ideas are extremely hard to test directly. It is not easy to design an experiment to confirm we live in a simulation, or to see the edge of a multiverse. So some critics argue that part of theoretical physics is drifting too far into abstraction. They worry that untestable theories can turn science into speculation. But even that criticism must face a truth. The most successful theories like quantum mechanics were abstract and counterintuitive from the beginning. Strange does not mean wrong. Perhaps this is a natural step in the growth of knowledge. Many ideas were once seen as extreme before technology became powerful enough to test them. What sounds like philosophy today may become the foundation of science tomorrow. And here, the remaining question may not be, is it true immediately? But does it scare you? Or does it make you excited? If you want, leave a comment below. If you liked this journey, please hit like and subscribe to the channel. Thank you for listening.